recording. All right. So you should know the parts to an atom, at least on the, well, subatomic level, but not the subatomic level. And so we have electrons, neutrons, and protons. Electrons, what's so special about an electron? What's one thing that's special about an electron? Negatively charged, okay, and neutron is neutral, and the proton is positive charge. What about, as it mentions here, remember roughly the mass of a neutron and the mass of the proton are equal, around 1 ADMU, give or take, roughly equal to each other, whereas the mass of the electron is deemed negligible. It's like 1,800 and some odd 36th the size or something ridiculously tiny. So that's usually whenever you're figuring out the mass of an atom, they just ignore that. Now there are other subatomic particles, okay? And so, which I don't think that, well, I know that for anyone who had Dr. B, she never covered nuclear chemistry, and I don't think that Dr. Duncan had time to cover nuclear chemistry either last time. But does anyone know what happens, or what's it called whenever an electron becomes positive? You have like positrons and all these little things that go on. And so this is part of nuclear chemistry. And so I actually I used to have a faith integration little thing that I got to talk about how, you can convert something evil into something good. But it's one of the few times I got to do faith integration. And so, yes?
Is this PowerPoint or the book?
Pardon?
Is this from the PowerPoint or book?
This is on, well, it should be on, I don't know if it's exact figures of the book or not, but it is on the PowerPoint. I think so. Okay. Now, in general, just to quickly review, we have, I would expect you to know how to read the chemical formulas of things, and if I give you an element, for example, and I want you to know the first, 20 or so, many of the elements you probably already recognize, and the ones in organic chemistry, what are some of the elements that you think that we're going to be using a lot of in space, organic chemistry, not in inorganic chemistry? Carbon, that's the number one, so you should know carbon. Oxygen, hydrogen, nitrogen, and there's one more that we'll talk about, especially more next semester, but also, oh, there's already carbon, but sulfur, that's another one that's biggie. But then we have all of our halogens. I would expect you to memorize the halogens. What are the halogens? What are the halogens? Fluorine, bromine, iodine, and chlorine. I don't know, because I didn't hear someone had said chlorine first. And I want you to know the relative positions on the periodic table. What's in this room, we already have it, but that way you can tell which one's more electronegative than the others, which one's larger, smaller, that kind of stuff, because trends are what's so important in organic chemistry. All right, so for example, if I give you because I don't have them all memorized myself, this, I would expect you to be able to tell me, first of all, what element is it? It's phosphorus. Secondly, what's the mass of this? The actual mass of this one.
15.
Is it 15 for the mass?
No.
No, it's going to be 33, but that's okay. Because when we're talking about this, because what does the 15 tell us? It tells you the number of protons. What else does it tell us if you need to learn? It doesn't tell us the number of electrons, necessarily. Well, it does here, in this instance, because one thing I didn't tell you is the fact that whether or not it's charged. This one is not charged. So then it tells you protons, tells you electrons, if you assume it's neutral, which you can. And then what about neutrons? How many neutrons are there in this one? 18. Okay, you subtract the 2. So this is the number of AMUs for this one would be 33. But what else? What other units can be used? That actually in organic chemistry and definitely biochemistry, we don't ever talk about AMUs. Does anyone know what units we use instead? When we talk about atomic weight. Because like if you're going to go and weigh out, of course you're going to be weighing out phosphorus, but you weigh out something that contains carbon on the scale, what are the units that you're using? You're going to measure out and say, okay, I'm going to do 458 times 10 to the 6th, AMUs. No, we use grams. And so what kind of units, how can we go from AMUs to grams? Like what was 33 here, 33 AMUs is equal to 33, not 33 grams, but 33 grams per mole. Tells you, that's why you have to make sure you know how to go between moles to grams, grams to moles, and so on and so forth from Jin Kim. All right, and so that's the kind of thing that I would expect you to remember from this. So, electrons, though, have this duality between them. And so they are so tiny that their mass is measured, but they also have a wave particle to them, but they also act like a wave. I know I didn't cover Hamiltonian operators in greater detail. If you go on to take physical chemistry, I'm sure that you'll cover it in much greater detail. But this is a Schrödinger equation. And the important thing here is just to know that every electron has both wave properties and it has both mass properties, okay? And so, because of the Heisenberg uncertainty principle, you can never know the exact location of something and how fast it's actually going. Okay, so you can only do, oh yes.
Could you go back to the last slide for a second? Yeah, so when you did the phosphorus, you had the mass number on the top, but in the ZMX thing, it shows the mass number on the bottom.
Oh, this may be a typo, because this isn't mine. So, but no, yeah, no, it's always the top. It moves, well, you usually put the larger number on the top. Yeah. All right. All right, so, but we're talking about the fact that you can never tell, because electrons, you can never think of it this way. They're so tiny, they're traveling so fast that you can't say that exact moment where that electron is located. We'll say what the Hamiltonian operators in Schrödinger equation comes up with is a probability of where it would be located at the point in time. And so this brought us to the quantum numbers. I actually don't like the way the book here describes the quantum numbers as well as I like to describe quantum numbers. And one thing I wanted to point out that if you look back in a lot of Jin Kim books, the second quantum number, it is called the orbital one. However, many books call it azimuthal or angular momentum. Okay, and so that's why if I say one of those terms or if you read it someplace else, those are interchangeable. The orbital is actually much more simple than the word azimuthal, but people can really remember what that is. It has to do with geometry. But we have the principal, the orbital and angular momentum one, the magnetic, and then the spin quantum number. And so, and then Pauli exclusion principle is the fact that no two electrons can have the exact same set of 4 quantum numbers. And so what I always like to say is I always try to explain it. It's sort of like an electron has a social security number. So each level, just like actually if you knew the social security number, when you break it down, the social security number tells you like what region the person was born in, and so or had applied for the card, and so on and so forth. Well, each section of that also tells you we have the principal quantum number, which is the N, the angular momentum, or what was this? The orbital one. Then we also have ipsum L and ipsum S. Okay, so this was the principal one, which tells you the energy level with which the electron resides. Does you remember, without cheating, looking ahead, what did the L, the angular momentum one, give you in broad generalities?
N minus 1.
And so it is. That's it. That's the maximum number of possibilities. So if n is equal to 1, then L is equal to 0. Okay? And so that is true. What does it tell you, though? Like, what does it really tell you in broad generality about what the energy orbital is going to be? The shape. Okay, and so, and whenever I taught Jin Kim, I just had you remember, like if it was a 0 versus a 1, and then it becomes much more complicated. But when 0, the simplest of the L's was what shape? The sphere. Because when you're talking about 3 dimensions, it's going to be a sphere. Whenever L was equal to 1, what was the shape going to be? Dumbbells is what I always called it. And then it gets a little bit more complicated from there. And it gets really complicated. Some of them look like pinwheels. Some of them kind of look like pinwheels with a little light preserver around them and all that kind of stuff. Or pacifiers and all that kind of things. But that wasn't so important as you just realized that the N told you which energy level it was located at. L gave you shape. this told you the energy level. Come on now, this is not wanting to write. It started to mess up on me earlier. Okay, and so we had spheres, we had dumbbells, then we have M sub L, which was called, that's the magnetics, not the magnetic quantum number. Does anyone remember what that one did? Usually people remember, or at least can remember one of the stories that I would always tell whenever I would talk about these two in particular. And so if we looked at just the outer energy level of carbon, so carbon has, if we look at the carbon total, how many total number of electrons does it have? Its atomic number is 6, so total, if it's neutral, it would be 6. But how many does it have in its outermost shell? 4, because the first 2 is like in that inner layer, you know, almost like the Tootsie Roll Pop, right? So 2 of them's in the little, it's protected, so we're just talking about the valence shell. And so there's 4. But many times people, at least whenever you're in high school or something, maybe you drew the energy levels like this. So we had the nucleus, and then we had 2 electrons, and then we had 4. And of course it looks absolutely nothing like that. It doesn't have that little bullseye look to it whatsoever. And so, come on now. It's like a delay. Instead, let me get a different color. Instead, we talked about carbon, and we're just talking about the last 4. Does it show up? For those of you who aren't colorblind, at least. What did it look like when we start to put the electrons in? Where does the first electron go? It goes here. Okay. Remember what was this orbital called? Yes, for carbon it's 2s. Okay. And then where does the second one go for carbon? If it's before it goes any bonding or anything like that, we're just talking about carbon, for example, as in graphite or diamond. For the second orbital, where does it go? I mean, second electron, where does it go? It goes in the same place, okay? And so here, let me change colors. That way we can see the orbitals a little better. I mean, the electrons. Because that would be the second one. Where would the third one go? It goes up to the P. And where does the fourth one go? To the next one over. Okay, so we only have 2 left here. Which one of these, what does this one tell you? I mean, I drew it out, but what does this one actually tell you? It has to do what were, and I actually used the term already, but what did each of these things indicate?
Energy level.
Well, this overall is an energy level, and then it's called, what is the word? That they're degenerate energy levels, because they're slightly different. This is all on the second energy level, so it's 2s and 2p after the p in it. 2s and 2p. But slightly different. In this instance, 2s is a little bit lower than the 2p's. Okay? Now, what were this? I always call them hotel rooms. You know, we had this hotel room and we had these hotel rooms. And so, but what's the actual term? Instead of hotel rooms, they are, starts with an O.
Orbital.
Orbital. Okay, so this one actually tells you the orbitals. It gives you the idea of the orbitals. Okay, that's why for this degenerate energy level, you only have one possible hotel room. But for this one, when it's the P's, it's M sub L. It had 3 possibilities, -1, 0, and 1. So that's where those come from. This one, whoops, there's only 0. The next one was -1, 0, +1, and so on and so forth. And then the final one, which was called the spin quantum number, what does it tell you? First of all, what are the possible values for the spin quantum number? -1/2 and +1/2. And what does it tell you? Right. It gives you, because we just roughly say, it gives you the magnetic moment. So if you think back to physics, you've taken physics, whatever, anything that's got a charge that it spins, which these do spin, it creates a magnetic moment. So they just randomly. They call one positive, one half, one negative, one half. It doesn't necessarily mean up and down, you know, because it's really moving around. But you have them in opposite directions or magnetic moments. And so that's the reason why there are only two possibilities, only two electrons at most can go into the same hotel room. That's when I would say that no one wants a third party in the hotel room, no one wants to take their mother-in-law with them on the honeymoon kind of thing. And at the same time, on the economic front, you always fill up all of the ones that are on the same degenerate level first before you start to double back. Okay, because if this was a hotel that you're trying to do, you're trying to maximize how many rooms you have occupied. And there were some exceptions. So for example, if you think back to zinc, is one exception, where it would have what it likes to do, not zinc, I'm sorry, copper, what it likes to do is rather than it have, was it 1, 2, 3, 4s2 and 3d9, it's better that it takes one of them and pops it up to where you actually have 4s1 and 3d10 because it just likes to have as many rooms filled as possible and things like that. And we talked some about the exceptions, and that's not as important here for organic chemistry. Okay, but that's what the quantum numbers tell you. And so we actually have already done this, but it kind of gives you an idea here. The big two tells you like the broad energy level, the big energy level at which it resides. The second one, the azimuthal or angular momentum, known as orbital one, gives you the idea of the shape. This one also tells you, I know they say, oh, it's related to shape and directionality, but if you think back to the P's, P is the easiest one to think of versus all those others, because in 3 dimensions, you can have dumbbells going 3 ways. On the on the x-axis, the y-axis, and the z-axis. And so that's why you could have, they're telling you then which one is which. Right? And then so on and so forth. Oh, that gave you the shape, and this one gave you the directionality for it. And then finally, tell you if it was one of the 1/2. I mean, once again, they don't. It's showing you 1 is equal to plus, 1 is equal to minus. It's just that they are dichotomous against each other. All right. And so we've actually already talked about this, how S is this one for sphere. Then we have, I always like to draw them out. I'll make it a little bit more obvious for whenever you do the hybridized orbitals, but you have the 3 possible dumbbells. Here we have along the x-axis, you have one on y and one on z. Okay. And then we have the off-bow principle, which is just a fancy way of saying how that they build upon each other. Okay, so that we've already done carbon. We filled up the first energy level, then you filled up 2s2, then we have 2px and 2py, and so on and so forth. And once again, at this point in time, that's about the extent that we're going to talk about it for here for the most part, except it didn't make sense for whenever it came time to bind things. And we'll talk a little bit more about how carbons and hydrogens come together, for example, to form an actual bond later on. Because what your book does is now it skips over, lets you know about that kind of thing, but then it talks a little bit about ionic bonds. Because there are different types of bonding. There was ionic bond, which at least for me was always the easiest one to explain. What's one of the other types of bonding? Besides ionic, we had covalent. What about another one? There's hydrogen bond, which is a specialized type of. What's another one?
The one that was like explained was like how lizards stick to walls.
The lizard stick to walls. Van der Waals interactions, which is a very Van der Waals interactions is one way of things that are intramolecular versus intra. And so that's why it's almost, we're just going to say that. I was trying to think of another way of talking about ones that are similar. They have in fact similar to ionic bonds, but they are not necessarily a positive charge versus a negative charge. And those are metallic bonds. So there are bonds that between metal ions, just think about like iron and copper and some of these. And that's how they conduct electricity. They form a special type of bond between themselves. And actually, we don't, here in Gen Chem, they usually don't cover it in great detail. It's because of the fact that, Gen Chem is supposed to be a broad exposure to lots of different types of chemistry. And then once you get into higher levels of chemistry, you would go into greater detail. But so a lot of times they just break it down to covalent, ionic, and metallic. And then, for example, hydrogen bonds and polar bonds are types of covalent bonding. For example, this is for example. All right, Coulomb's law. I'm not going to ask you to do Coulomb's law. And so, if one of the questions has to do with math, try your best to do it. But I won't ask you to do a math question on Coulomb's law. So that on the actual exam, I don't get to pick. I get to pick broad topics of what they talk about in the quizzes, but I don't pick the actual question. All right. So an ionic bond is really simple. It's just where you have something that, well, it's easier. With sodium chloride is always the easiest one to explain. You have a sodium, it's got 1 electron in its outermost shell. You've got chlorine, it's got 7. It likes to have that last electron be full. So sodium gives up this electron, chlorine takes it. You have a negative charge and a positive charge, opposites attract and come together. They are almost always soluble in polar solvents. I say almost always, so you'll find out in biochemistry that it's not always true, but almost always. And then they have high melting points. And so it's why if you try to melt salt, it takes hundreds, if not thousands of degrees Kelvin in order for them to melt. Okay. So this is just showing everything that I just talked about before. So I'm going to go pretty fast on this one. Now, one thing I wanted to point out here is carbon in of itself hardly ever will form an ionic bond. Okay? You just don't have to worry about it. In fact, whenever I first took organic chemistry, it was taught by a man who I'm sure is probably no longer with us because he was an old man whenever I took it. But Dr. Kaiser, he gave out what they call rules of thumb. And so he would always draw it, and so I'll just do one right here, for example. So you'll get used to it. Even though mine always look more like rules of big toes. It's supposed to be a thumb. All right, so the rule of thumb is whenever we're doing our mechanisms, and we're doing all of our, coming up with products and reactants and stuff like that, carbons will never be charged. Okay, in the final. You may have an intermediate, but a carbon will never be charged in the final product, okay? So that's just one rule of thumb to know. Carbons never charged, because they are not happy. Whoops. And then in your notes, you put one in final product. So we're going to talk about, you're going to actually see this. This is this is called alkyne. This is an alkynyl anion. They are very reactive. Okay. And so it's useful for synthesis. You can make this, and then it's not happy, so it's going to go on and react with something else. So that's one way that we build things. Later on in this semester and all next semester in lab, we'll be building things from organic synthesis. And so this is actually a useful tool. And so that's why this would be an alkynyl carbanion, but it's not going to be happy. So in the end product, it will never look like this because it just is too reactive. This one, on the other hand, this is ethoxide. As the oxygen is negatively charged, you can make ethoxides. They're still relatively reactive. Now, if it gets bigger and bigger and bigger, it actually becomes less and less reactive because of other things. And so they also can become synthetically useful as well, right? So that's what this is trying to say, is that, yes, covalent. This is a covalent bond within the molecule. Intramolecularly, it's covalent. This would be intermolecularly an ionic interaction. But I'm just telling you right now, this would not ever be your final product, okay, for the process. Right. Then they have what they call nucleophilic, and then there's something called electrophilic. Nucleophilic literally means, what does philic part mean? Love, the phile, like a bibliophile loves books, Anglophile loves the English culture. Nucleophilic, what you suppose it's going to love? A nucleus. And so, for example, this is nucleophilic, this is a nucleophile, because it's going to go like so, and this one's really strong nucleophilic. It's a nucleophile because it's going to want to go love and smack into a nucleus of something else in order to make a new bond. Okay, And the opposite of that is electrophilic. Okay, something that wants to love the electrons. And so nucleophilic is what's electron donating, you make a new bond. Electrophilic is what's going to accept those electrons. Right. Then we have the Lewis model. I've actually covered this. Whenever the electrons are not shared equally, so for example, this is hydrofluoric acid. Fluorine is the most has the highest electronegativity. Hydrogen, it's not the lowest. Its position on the periodic table kind of lies in where you think it would be, because it's roughly the same as carbon and boron. And so, but it doesn't like electrons nearly, I should say, it doesn't want electrons nearly as much as the fluorine does. And so because of that, it's like those kids you probably knew growing up where they were stingy with their toys. And so this one's stingy with electrons, it draws all the electron density closer to it, so it leaves more a disparity of the electron density here to where the hydrogen side is more positive than what you would expect, and the fluorine side is more negative, but they are not two separate entities here. And so because of that, rather than giving it a formal charge of +1 and a -1, they give it just like in math, where if you think back to math with like a derivative means a small change, you get that little delta, the little d form. So it's slightly positive and it's slightly negative. And so then it's called polarized. Then we had the Lewis structures. And so what we did was we added up all of the valence electrons. You had to take into account whether or not it was ionic. Because remember, if it's negatively charged, it means it owns even more electrons than you'd expect. If it's positively charged, it's giving up those electrons. Okay, and then what you do is you just figure out the best way to position those atoms with their electrons around the central molecule. Okay, almost always, if you have more than 2, the less electronegative atom will be in the middle. Okay, it becomes a little bit more difficult once we have, say, like 18. But when we're talking about 3 or 4 atoms, and we're talking about the one that's less electronegative will be in the middle typically. Okay, so there are exceptions, but typically the one that's less electronegative will be in the middle. So let's just do an example. All right. Okay, let me make this a little bit bigger. So we have, for example, oh wait, let's make it more simple and we'll go up from there. Let's see. There we go. So by the way, this is difluoromethane. You'll learn how to name it, I think next chapter. You'll learn how to name it soon. In case you can't tell, it's H2CF2. So I'll give everyone a moment to try to draw the Lewis structure. And this time, many times I draw in organic chemistry, we ignore drawing in all the lone pair electrons, but this time at least we want to. Okay? Just like in the future, many times they don't always draw in the lone pair electrons and oxygens, they're just assumed. You just learn that oxygen likes to make X number of bonds, carbon likes to make X number, so on and so forth. Whereas in Gen Chem, usually we draw everything in. By this point in time, you're supposed to just to realize that there are some things that are assumed for clarity's sake. Okay, so what's going to be the central atom here? Yeah, the one of the 5, which one's going to be in the middle? Carbon. Okay, and so we know that there's going to be, it has to make the bonds to H, F, and F. Now, if you remember from Gen Chem, how many total number of valence electrons are there for this molecule? And how do we, or how do we go about figuring out how many electrons we need to put in?
20.
I mean, how do you come up with that number?
Looking at the periodic table, we just count to the right. So for hydrogen, each one has one of its own.
Okay, so that would mean there's 2 from hydrogen.
For the carbon, there should be 4.
Yes, there's like a delay in the pen. Okay. And
7 for fluorine.
right, for each one. All right, and so that gives us a grand total of 20. So there are certain things that we already know. Change colors. The carbon has to be making at least one bond to each of these. Right, 1, 2, 3, 4. So how many electrons have we already used up? 8. So therefore we have how many left? 12. So where do we put those 12 electrons, and how do we put them?
Around the fluorine.
Around the fluorine. Okay, and that's where I'm going to draw them in. It's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. Why do we know that hydrogen doesn't have any? What's the maximum number that can be around the hydrogen? The maximum number. 2. And it already has 2 that it's sharing with each of these. So whenever you're in a hurry and you're drawing, don't litter. Whenever you're in a hurry and you're drawing these, the way to, not to cheat, but the shortcut way, is the hydrogen should only be making one bond, okay, at most. Carbons make how many bonds at most? 4. And so that's why it's easy. How many bonds usually do fluorines make? How many bonds usually do they make? 1. And that's true with all the halogens. Now you will find out at times it is possible to have a double bond there. It's just not usually not happening. A double bond with the fluorine, but it's just usually not happening. So it is in theory, especially true for like bromine and some of those later further on. But in theory, typically if you're in a hurry, halogens you just draw one bond to. Carbons you want to have a total of 4. Hydrogen you want to have a total of 1. Whereas, how many, do you remember for a nitrogen, how many total bonds does it usually like to have around it? 5. In oxygen, well, I mean, so how many total bonds around nitrogen, first of all, that's not total number of bonds. How many total bonds around nitrogen does it like to have? Many times, not always. So think, what's a nitrogen, a common nitrogen containing compound? Ammonia, right? NH3, and so how many bonds does it have? 3, right? Because it's got a lone pair of electrons, and so that's why. It likes to own 5 electrons, which we're going to get to that in just a moment. It likes to own 5 electrons, but many times it makes 3. Now, there are exceptions, especially for nitrogen. How many bonds are usually around an oxygen? 2. And why is it that oxygen usually has just 2? How many electrons?
6.
Because they're usually, if we're making 2 bonds to an oxygen, how many electrons are left over? Someone said that is 6. How many electrons are usually left off from making 2 bonds to an oxygen? 4. And those are lone pair electrons. How do we know that? What's that called? That fluorine has those, and oxygen would have 4 lone electrons and things. So what's that rule called?
Octet.
The octet rule. And so there's the duet rule and the octet rule. There are times that you can violate it. Anytime you get below in the third level or below, you can violate it. Okay, especially with having either more or less, or some things like boron can have 3 and aluminum can have 3, but you can have 6. I'm sorry, supposed to make 3 bonds. But typically, many times we follow the octet rule. Carbon always wants to follow the octet rule, or it's not happy. Hydrogen, though, can only follow what's called the duet rule. Hydrogen, helium, what else follows the duet rule? Lithium. So yeah, lithium follows the duet rule too whenever it can follow the duet rule, because then you can't put in in beryllium if it forms an ionic bond, then it's going to actually look more like helium. All right, so let's do another one. Let's go. Whoops, I did the wrong one. There we go. Let's see. All right, so I'm going to do give everyone a moment to try to figure this one out. By the way, this one, let me see if I can draw it in my head real quick. The common name is called formic acid, but it's methanoic acid, or not acetic acid. Methanoic acid is formic acid, yes. So what will be a central atom here? So we have a carbon, so we'll draw the carbon in. Okay. So now there are multiple ways. First of all, what's the total number of electrons that we're going to be wanting to deal with?
18.
Okay, so we have 18. All right, so what are some of the atoms that the carbon should be touching? Pardon? So we have oxygen. So I'm just going to draw oxygen here. What else could we have around here? We have hydrogens. Whoops, there should only be one. Okay, hydrogen, we have a hydrogen. We have an oxygen. Now, if we draw it this way, does it work? No. I mean, you on your own, when you have more time, you can draw it. Yes, you can make it to where this has the hydrogen would be perfectly happy. You can make the single bonds here, but then what's going to be the problem here? What will be happen to these oxygens? Then lots of electrons around them. They have too many. Plus, we're going to get to the idea of formal charges. They'd be charged, and overall, this is not charged the way it's drawn. So that means something has to be rearranged a little bit. Okay. So what's one of the first things that's relatively easy for us to, it would be good hypothesis that is not touching the carbon? Mm-hmm.
Move one of the hydrogens to the other side of one of the oxygens.
Okay.
You do it for both oxygen.
So now, let's start drawing in, I'll change the colors for those who aren't colorblind. Right? We still would expect at least one bond between all of these. Okay? But what must be true? The hydrogens would be happy. But what, just looking at right now, before we put in the lone pair electrons, what's not happy?
The lone oxygen.
So we would have the lone oxygen's not happy, which we could put, how many do we use? 1, 2, 3, 4. 4 times 2 is 8. We only have 10 electrons left. So we could put 6 and 4, and that uses up all 10 electrons. But what's going to be unhappy? I didn't draw any stuff about it.
Carbon.
The carbon's not. So what must be true about this carbon?
It needs no more bond.
It needs another bond. And where can it have another bond to?
With the lone oxygen.
Yes. So now we've used up 2, 4, 6, 8, 10. So there's only 8, or there are only 8 electrons left. Now we put in our lone pair electrons, because we want all of the oxygens should have a total number of how many electrons around a grand total. Like, so if we take what I'm going to call the top oxygen there, how many electrons currently are around it? 4 total. Okay, so how many lone electrons does it need? 4. 1, 2, 3, 4. Likewise, how many are needed around the other oxygen? 4. And now please note that this is not geometrically correct, but lo and behold, this is it. So that's what formic acid looks like. By the way, this is called carboxylic acid. Because you should start to memorize. I'm preparing you right now. I think this is in chapter 4. Is a table that's got the the functional groups. And in order to know organic chemistry, you have to know, just like to read, you have to know the letters to read. For organic chemistry, you need to know your functional groups. You have to know for biochemistry as well. And so, it used to be table 4.1, but I'll look at the exact number. I'm still waiting for my physical book to come in myself. But you want to look at it and just print off, or you can even print off like a table of organic functional groups. And I'll even try to make one available on my Fire stuff, but you don't have to try to scan and search and everything for it. But I have to use an older book to do it. And the reason why you should want to start memorizing now, I think it's like within a month or so down the road, I will every single quiz and quiz that we take in class, and every single exam that we take will have questions about functional groups. And that's not true just for organic Q1, but also for organic Q2. So just now, start thinking about it. This is a functional group called carboxylic acid. Okay, so this is the simplest of the carboxylic acids. All right. And we want to check formal charges. You always check the formal charge. And to do that, what you do, for the last thing, every time you draw one of these, is it's easy to tell for carbons and hydrogens. It's really simple to tell the formal charge. If a hydrogen is making one bond, it's neutral. If a carbon is making a grand total of 4, it's neutral. Okay, because carbons came into the relationship having 4 electrons, I'm sorry. It actually owns, for electronic bookkeeping, 1 from each of these bonds, so 4 minus 4 is 0. Whereas if we look at it, let's sit with this oxygen. What's the formal charge of this oxygen? How many electrons did it have when it was by itself in its valence electron down its shell? It's 6. In this configuration, how many electrons does it own? 6. 1, 2, 3, 4, 5, and 6. And so, and if you check it out with this